There is a number that seismologists in St. Louis, Memphis, and Nashville do not say out loud in press conferences. 8.0. That is the magnitude of the earthquake that the New Madrid seismic zone, a buried fault system stretching more than 150 miles beneath the American heartland, is fully capable of producing. Not in some distant geologic future. Right now, today, in the next 5 minutes if the fault decides it is time. And the terrifying part is not the number itself. It is what sits directly above it. 12 million people live within the immediate impact zone. Memphis, Tennessee, a city of 600,000, is built almost entirely on top of loose river sediment that will behave like liquid during a major shake. St. Louis, Missouri, sits 60 miles from the fault's northern end. Nashville, Little Rock, Jackson, and Evansville all fall within the shaking radius of a great earthquake. And unlike California, which has spent 60 years and tens of billions of dollars preparing its earth, cities for the earthquakes its geology promises, the American Midwest has done almost nothing. The bridges are old. The gas lines run under streets that will rupture. The hospitals are unreinforced. The warning systems are minimal. And the last time this fault truly woke up, it rang church bells in Washington, D.C., and reversed the flow of the Mississippi River. But here is the detail that tells the real story. Almost nobody in those 12 million people's lives has ever been told this fault exists. To understand what is really hiding beneath the cornfields and river towns of the central United States, you have to go back to a winter that people living through it believed was the end of the world. On December 16, 1811, at approximately 2:15 in the morning, the ground beneath what is now northeast Arkansas shook so violently that it was felt from Canada to the Gulf of Mexico. The estimated magnitude was between 7.5 and 8.1. Then, 6 hours later, it happened again. A second earthquake, nearly as powerful as the first. Then a third the following day. Then a magnitude 7.4 on January 23rd. And then, on February 7th, 1812, the largest earthquake of the entire sequence, estimated at 8.0 or higher, tore through the same zone. In total, the New Madrid seismic zone produced 4 major earthquakes in less than 60 days. Over 2,000 aftershocks rattled the region across the following year. Scientists studying sediment records believe the sequence was comparable in energy to anything that has ever struck the continental United States. The ground opened in fissures. Sand and water blasted out of the earth in jets that locals called sand volcanoes. Fountains of liquefied sediment shooting into the air from fields and riverbanks. Entire forests dropped several feet into the ground as the soil beneath them collapsed. New lakes formed where none had existed before. Reelfoot Lake in northwest Tennessee, a lake that still exists today, stretching 15 miles across, was created in hours when the ground sank and the Mississippi River temporarily flooded the depression. There are eyewitness accounts of the river running backward for hours as the seismic waves passed through it. The vibration was so powerful that it rang church bells in Boston, 1,100 miles away. Ships on the Mississippi reported the river foaming and roiling as if it were boiling. Flatboatmen floating goods downstream described a roaring so loud they thought the world was coming apart. And at the time, the population of the entire region was perhaps 3,000 people. Remote river settlers and Native American communities in sparse woodland. Today, that same fault sits under one of the most densely connected infrastructure corridors in the country. Here is the problem that is not making headlines. The soil that makes the New Madrid zone so deadly is not solid rock. The entire Mississippi River Valley, from Cairo, Illinois, south through Memphis to the Gulf of Mexico, is built on a deep layer of alluvial sediment. River deposits accumulated over millions of years, silt, clay, sand, gravel. When seismic waves pass through saturated loose soil, a process called liquefaction occurs. The ground loses its structural integrity. It behaves like a fluid. Things built on top of it sink, tilt, or topple. Foundations crack. Underground pipes shear apart. This is not a theory. In 1906, San Francisco's Marina District, built on bay mud and debris fill, liquefied during the earthquake and dropped whole apartment buildings into the ground, while neighboring blocks built on rock stayed standing. Memphis sits on a layer of river sediment, in some places more than 100 feet deep. That sediment runs directly beneath the city's water treatment plants, gas distribution network, hospital foundations, and bridge abutments. The bridges are the part that keeps engineers awake at night. There are 8 major highway and rail bridges crossing the Mississippi River between St. Louis and Memphis. The Army. Corps of Engineers and USGS have both conducted studies modeling what a major New Madrid earthquake would do to those crossings. The results were classified for years before the summaries leaked into academic papers. The projections were stark. Most of the bridges in the zone were built before modern seismic codes existed. Several were built before World War II. A magnitude 7.7 earthquake centered on the New Madrid Fault, an event that USGS considers a realistic scenario, would potentially collapse or severely damage the majority of those bridges. Once they go down, the supply chain for the entire eastern United States fractures. Interstate 55, Interstate 40, the rail lines that carry grain from the Midwest to the ports, every truck, every train, every fuel pipeline that crosses the Mississippi River between Cairo and Vicksburg would be severed or compromised. FEMA has modeled this scenario. They called it the most expensive natural disaster in American history by a significant margin. Estimated economic losses in a major event? Over $300 billion in the first year alone. If you are finding this useful, hit subscribe. We cover earth science events, infrastructure crises, and geography news with the full depth you need to actually understand what is happening. But the bridges are only the beginning. Memphis's water and gas infrastructure runs beneath streets that would liquefy. The city's main water intake and treatment facility draws from the Mississippi River, and its pipes extend underground through neighborhoods sitting on sediment that would shift and crack during a major event. A USGS hazard assessment found that a magnitude 7.7 New Madrid earthquake could leave Memphis without running water for weeks, possibly months, while emergency crews tried to identify and repair hundreds of broken mains across a city whose roads would themselves be compromised. The hospitals that would receive the injured are many of the same buildings that cannot safely treat them during a major seismic event. A 2009 study by the Mid-America Earthquake Center found that a large New Madrid earthquake would critically damage or collapse roughly 3,500 buildings in Memphis alone, including a significant percentage of the structures designed before seismic standards were adopted in the 1990s. And Memphis is not even the most vulnerable city in the zone. Cairo, Illinois sits at the confluence of the Mississippi and Ohio rivers, directly above the northern end of the fault. It is a small city now. Its population collapsed over decades from over 15,000 to fewer than 2,000 as its industrial base eroded. But Cairo is surrounded by the New Madrid floodway, an emergency channel that the Army Corps uses to divert the Mississippi when floods threaten. Beneath Cairo, the sediment is extraordinarily deep and saturated. USGS hazard maps give Cairo some of the highest liquefaction potential of any area in the United States. The city sits in a bowl formed by levees on all sides, levees that a significant earthquake could compromise. After a major New Madrid event, seismologists worry that Cairo and the surrounding lowlands could face a compounded catastrophe. Ground failure from liquefaction, followed by flooding, if levee integrity is compromised. The scenario is not hypothetical. It is the modeled outcome that federal planners use in their worst-case planning documents. Now here is where the timeline gets harder to ignore. The New Madrid seismic zone does not produce one great earthquake per century and then go quiet. The geological record, read through paleoseismic trenching, digging up ancient ground disturbance, and reading the layers the way historians read documents, shows a recurring pattern. Scientists at the USGS and at universities across the Midwest have identified multiple sequences of New Madrid earthquakes going back over 2,000 years. The evidence suggests major events clustered around the years 300 AD, 900 AD, and then the 1811 to 1812 sequence. That pattern implies a recurrence interval of roughly 400 to 600 years between great earthquake clusters. A cluster that last fired in 1812 is now more than 210 years in the past. The fault is roughly 1/3 to 1/2 of the way through what the geological record suggests is its typical quiet period between major episodes. But here is where the scientists disagree in a way that should sharpen your attention rather than dilute it. A group of researchers led by Seth Stein at Northwestern University published a series of papers in the 2000s and 2010s arguing that GPS monitoring of tiny ground movements shows the New Madrid fault is moving much more slowly today than the 1811 earthquake rate would imply, and that the fault may be slowly shutting down over geologic time. Their argument? The stress that drove the 1812 sequence may be largely spent, and the zone may not generate another major earthquake for thousands of years. The counter-argument is every bit as alarming as the original concern. James Ho, a USGS seismologist whose career has been built on studying the New Madrid zone, and others who have worked the paleoseismic record, argue that the pattern in the ground does not match Stein's interpretation. They point to the trenching data, the sand blow evidence, the recurring 400 to 600 year signal in the sediment layers. They point to the fact that the zone continues to produce small to moderate earthquakes at rates far above background levels. They point to a simple fact: a fault that produced an 8.0 earthquake 210 years ago and continues producing measurable seismicity today cannot be declared dead on the basis of slow GPS movement alone. The argument is still unresolved. What is not unresolved is this: regardless of which group of scientists is right about the timing, the cities above the fault are almost entirely unprepared for the event. Both groups agree the fault is capable of producing. The human picture beneath those statistics has a name and a face. In the small towns of the Missouri Boot Heel, Sikeston, Poplar Bluff, Cape Girardeau, many of the residents have never heard of the New Madrid seismic zone. They live in unreinforced masonry homes built before World War II. Their local water towers are unbraced. Their hospitals are two-story brick buildings from the 1950s. A major event in those communities would not just break buildings. It would eliminate the emergency response capacity at the same moment the emergency happened. FEMA's 2011 national level exercise, called New Madrid Full-Scale Exercise, simulated a 7.7 magnitude New Madrid earthquake and modeled its effects across 8 states. The conclusion was blunt. The event would exceed the capacity of any state or regional government to respond alone. The federal government would face a mass casualty, mass displacement, critical infrastructure failure scenario simultaneously in multiple states. The exercise found that even reaching the affected communities would be the primary challenge, because the roads and bridges that emergency responders need to cross, the same corridors that commercial supply chains depend on, would be compromised or gone. And sitting beneath all of it is a geological mystery that has never been fully explained. The New Madrid seismic zone does not exist where it should. The theory of plate tectonics predicts that the great fault zones, the places where earthquakes occur, should sit at the boundaries between tectonic plates. The San Andreas Fault marks the boundary between the Pacific Plate and the North American Plate. The subduction zones off the Pacific Northwest coast mark where the Juan de Fuca Plate dives beneath North America. The New Madrid seismic zone sits in the middle of the North American Plate, hundreds of miles from the nearest plate boundary. It is what geologists call an intraplate seismic zone. The prevailing theory is that the zone sits above an ancient failed rift, a place where roughly 500 million years ago, the continent began pulling itself apart, failed to complete the process, and left a buried zone of weakness that still responds to distant stresses in the plate. The Mississippi Embayment, the geological depression that holds the lower Mississippi River Valley, is essentially the scar of that ancient failed rifting, filled with river sediment over tens of millions of years. The fault still moves because the stresses driving the North American Plate from its boundary zones transmit inward across the plate and concentrate at old zones of weakness. The rock buried deep beneath Memphis and St. Louis is still, in some sense, the unfinished business of a continental breakup that failed 500 million years ago. That is what lies beneath the cornfields and river towns. A 500 million year old wound in the continent's core, last torn open in 1812, waiting in the middle of the most underprepared major urban corridor in the country. The question number seismologists will answer on camera is not whether the New Madrid seismic zone can produce another great earthquake. The geological record has already answered that. The question is what happens when a magnitude 8.0 earthquake strikes Memphis, Tennessee, in a world built for California-level preparedness in California, but built for nothing in the Midwest? What happens to the Mississippi River crossings when the bridges come down and 12 states east of the river lose their primary supply routes simultaneously? What happens to the levee systems in the Missouri Boot Heel when the ground beneath them shifts and the Mississippi runs where it was not supposed to run? What happens to the families in the unreinforced brick homes in Poplar Bluff and Sikeston and Dyersburg when the walls come down at 2 a.m, the way they did the first time in 1811, when the population of the entire region was measured in the thousands? The fault has been quiet since 1812. It has not been idle. Small. Earthquakes rattle the zone dozens of times per year, most of them too small to feel. The sediment above the fault retains the record of everything that happened before. Sand blows still visible in farm fields across Arkansas and Missouri, frozen in the earth like a receipt from the last time the fault announced itself. They are still there if you know what you are looking for. Circles of pale sandy soil amid the dark river loam. Markers left by the last time the ground here behaved like a liquid, and the world above it had to be rebuilt from almost nothing. The river still flows south. The bridges still carry their traffic. The cities are still standing above the fault, the way they have been standing for 2 centuries, built on sediment that remembers what it can do. And the fault does not care how many bridges cross it, how many water mains run beneath it, how many hospitals were built above it, or how many people never learned its name. The math under the quiet has not changed. It never does.